Welcome to a lesson with Dr. Powell. Let's take a look at two practice problems that deal with just using a derivative of a function to answer a simple question. So suppose that we have a rabbit population, which is modeled by the following function. The output tells us how many rabbits there are at a particular year, where t is going to be measured in years. Okay. All right. So if you think about it, I mean, every time t is a multiple of 5, we're going to have a whole exponent up here. So after 5 years, it's like we're multiplying by 3. After 10 years, we're multiplying by, well, 3 squared, and so forth. So every 5 years, we're multiplying by another 3. In other words, the population triples every 5 years if you just look at this. That's just a side note, just so we can understand kind of what's happening here with this function. And when t is equal to 0 in particular, this is 3 to 0 is 1. So we're starting with 100. So there's 100 rabbits to start, and every 5 years, we're multiplying by another 3. So it triples every 5 years. It can be represented by it. This is a nice exponential function, represents that growth rate, or that growth. But in particular, I want to know what the growth rate is. Now, what is growth rate? That's another way of, if you like, by just saying, at least here, I haven't said exponential growth rate. I haven't used any other adjectives here. If I just say rate or growth rate, usually, if I haven't used any other adjectives, that just simply refers to rate of change. Rate of change of output to input. In other words, derivative. Okay, so rabbits per years. Okay, so that's really what I'm looking at, and instantaneously at that moment in time. So rabbits per year instantaneously, how is that changing right when t is equal to 10? So I'm looking for an instantaneous rate of change. Now on the curve, between two nearby points, that'll be different than the actual tangent line slope. But I'm interested in this tangent line slope. What's the instantaneous rate of change right at that moment in time, right at 10 years, exactly right there. So, well, what we can do is we can take a derivative of this. All right, so this is a constant 100 multiplied by this exponential 3 to the t fifths. All right, so in a derivative, let's think. This is just a constant multiplied on that stays there. Take a derivative, so that'd just be 100 times the derivative of this part. Well, what's the derivative of a to the x? Where a is a constant. It's ln of a times a to the x. So we could think of this as being ln of 3, the base, times, and then we have just 3 to that thing. But we're taking with respect to t. This is t fifths, so then we have to multiply by the derivative of what's inside here. T fifths, derivative of that's just 1/5, because t over 5 is the same thing as 1/5 over t, and the derivative of that with respect to t is simply 1/5. All right, so we just computed the derivative successfully for this, so we can use this derivative function, evaluate it right at 10 to see what this would be. So if we plug in 10, that'll give us the instantaneous rate of change that we're interested in. So we have 100 times the natural log of 3 times 3 to the 10 over 5, so 3 squared, times a fifth. So that's 9. That's 900. That's 900 natural log of 3 all over 5. Now keep in mind 2.7 raised to what power is 3? I mean, just a little bigger than 1. I mean, this might be close to 1,000-ish. I mean, it's a little more than 900 over 5. I'm just kind of guessing, estimating here a little bit. But if you thought of this as it's probably, I have to plug it in. But anyways, but if you think about it, 1,000 over 5 is about 200 or so. So maybe like around, give or take, maybe less or whatever, 200-ish rabbits per year is the increase every year at that moment in time, just instantaneously. So if I went 1 year off, or so if I took the average rate of change over that next year, it from year 10 to year 11, it would be that average rate of change would be hopefully close to the instantaneous rate of change. So the instantaneous rate of change right there would be an estimate for what that average rate of change would be during that year. So that was question number 1. All right, let's look at another one. What about with projectile height? Okay, so something being launched or whatever else, maybe perhaps it has some kind of function. This is a height function, okay, how high it is at a moment in time. Maybe time is measured in seconds here, and the height, let's say, is measured in meters. Okay, so meters above the ground or something like that, and time is measured in seconds. So vertical speed, what's speed? Well, their units are meters and time is measured in seconds. So that would be, so speed going upward, meters per second. So I'm looking for how many meters it is every second instantaneously. So vertical speed at that point. At a point, that's usually referring to an instantaneous rate of change right there. How fast would the speedometer, the upward speedometer, read right at that moment in time at 1 second? How to do that? Just take a derivative. Take a derivative of h. So h prime of t would be equal to, so 2 times that. So we'd get, 9.8. So negative 9.8 t. So the 2 comes down and drop that exponent. Here it's just plus 100. So there's the derivative. So how do we find the vertical speed at 1? Instantaneous rate of change at 1. You just plug 1 in, right? So to answer part A, and remember, use the units, meters per second, h prime of 1 would be equal to just simply negative 9.8 times 1. So just leave it like that, plus 100. So which would be equal to simply 90.2, right? So 90.2 meters per second right at that moment. All right, let's look at the next part. What time will h of t reach a maximum? So let's think about that. So the height, this is a projectile going upward. If it was going like up and then down, think about it. What happens right at the top? What's the velocity going upward? Well, right instantaneously, right at that moment in time, you should expect a velocity of 0. I mean, velocity should be decreasing along the way. In fact, you can even check it. Let's see, at 0, when you plug in 0, what's the velocity? Velocity is like speed with a direction. Here it's vertical and we're going up or down, positive or negative. Right here, velocity would be 100 meters per second. So notice how it's going down 1 second later. So it's going to keep, velocity upwards going to keep going down to a point. And when the velocity, upward velocity becomes negative, that means it's going down. So when it switches from up to down, that's going to be 0. So you think, okay, so where is the velocity function? So for part B, we think, where is this velocity function equal to 0? Negative 9.8 t plus 100 equal to 0. Like, we could easily solve for that. You could, let's just add 9.8 t on the other side if we want. 9.8 t, that's positive, 100, so divide by 9.8. So 100 divided by 9.8 seconds. So a little more than 10. So a little more than 10 seconds, it'll reach a maximum. And there we've just finished both practice problems on that. Thanks for watching.